Hello, good morning, everyone. Sorry for the delay. There were certain issues. Anyway, so we'll start with the lecture. During the last lecture, I sort of touched upon certain aspects around analog to digital conversion and things like that. So I thought we'll have a bit more detailed look into that in today's lecture. And then later on, the latter part of the lecture, we'll also look at some of the various hardware components and things that we may interface with when we are building embedded systems. So that's the main two things that we'll be focusing on today. So when we think about analog and digital systems, the main computational components of embedded systems, the computational components that we have discussed so far in this course, are digital systems. Or rather, they are digital computing systems. So all the computational aspects of these systems are in the digital realm. But when we think about various other systems that we may want to interact with, when we think about various embedded systems and things that we may want to interact with, those would be, a lot of them would be what we could classify as analog systems. So when we think about it from the perspective of our digital computers or the digital computing systems that are going to be central to our embedded systems, we would have to do a couple of things. That is, we have to receive input from these analog systems and then convert them into digital form so that we can process them in our computers, in our computer systems. Then at certain times, if we want to control these analog systems that are external to us, we may want to produce some analog outputs from our digital information. So again, we may have to do the reverse conversion from digital to analog. So these are the things that we will be sort of touching upon in a bit more detail today. So when we think about systems like in a sort of a embedded system environment, let's say we will start with something in the analog world that would produce an analog signal. Then we'll do some form of conversion to get it into a digital signal. Then we will have our digital computers, signal processors and whatnot, which can do processing, computation, calculations using the digital signal. Then once that is done, if you want to do some further controlling of these external analog systems and we need to forward information to those systems, we will have to again convert it back into analog information through digital to analog conversion and produce analog signals that can be forwarded on. There would be other various components like filters and such, which we will not be focusing in this part. You may come across those when in signals and systems and modules like that. So when we think about analog signals, analog systems, and the information that is being produced by analog systems, we would identify that as an analog signal. So the main point about analog signals is they are going to have continuous values over a period of time. So if you're observing over a period of time, they are going to have continuous values. So that is, say, if we observe the speed of a vehicle, so if you are observing speed of a vehicle, at every moment in time, it has a valid speed. So the only thing is we will have to plot it depending on the speed changes. It may change, but at every moment in time, it will have a valid speed and it is continuous. The value will be valid continuously as long as that system is active or that signal is being produced. So it will be a continuous signal. Then the other point is analog signals will have infinite range of values. So that is, say, if you increase the speed of your vehicle from, say, 10 kilometers per hour to 20 kilometers per hour, when you are increasing the speed, you will increase through all the possible values between 10 and 20. You are not going to increase in steps like 10, next 11, next 12. Likewise, you are not going to go in steps. You are going to go through all the possible values in between those two. In observation, you may see some of these values. Say in a speedometer, it may only display some of these values. But in reality, the vehicle speed is increasing through the infinite ranges of values that is possible there. And also because they have these infinite ranges of values and they have these continuous values all along a period of time, what we will have is we will have more exact values in such a system. So even if we think about the speedometer of a vehicle, if it is displaying a particular value, say it is a digital speedometer and it is displaying it in as a digit, the speeds, it is going to somewhat approximate that into a nearest full number and display that. But the reality is the speed is going to be not like that. It is not going to be 10, then 11 and 12. So it is going to go through all those infinite ranges. And the actual signal is going to have these more exact values. So that is the point about analog signal. And for examples of analog signals, it can be any physical phenomenon that we can observe. So things like intensity of light. So the light intensity is getting, say, from darker to lighter, brighter. So there it is an analog signal. Sound, when we are speaking, all these things, these are analog signals. Pressure levels, temperature levels, or any sort of physical phenomenon that we can observe, we can observe that in the form of an analog signal, as long as we have suitable apparatus to observe that. So the main advantage of having such analog signal is this. So when we have analog signals, we will have infinite amount of data. We will have infinite amount of values that we can use. So because we have infinite amount of data, that means we have a lot of information as we need. Then the density of information is also higher. So when we think about it, we will have infinite amount of data from the time point of view, so that is the density. Then also from the intensity point of view also, we will have infinite amount of data. So all along both axes, we will have a lot of data. And when analog signals are processed as analog information, it is also fairly easy to process. So that is also something that that we would observe. That is, analog signals are easy to process in analog systems. So not doing the conversion, but as in those systems, it will be easy to process. But some of the main disadvantages with analog systems would be they are prone to noise. So that is, say, if we think about analog, say, signal being carried over a medium, like say wire. So we have audio signals being carried over through a wire. And if there are external magnetic interference, for example, this analog signal would be significantly affected. And the longer that we transmit this, the more it is going to be impacted by noise. So if we are fairly closer, then the impact would be less. If we are traveling much further, then the impact would be much more. It would be impacted a lot more when it is traveling over a long distance. For example, a good example of an analog signal could be speaking or sound. And we know that sound can get disturbed by external noises, or even like in a sound sense itself. It doesn't have to be any other form of noise, sound itself. So over a long period of time, other sounds in between can interfere with that signal and impact upon what other person may hear at a longer distance. Then similarly, another bigger issue again that we can see with sound as an example, the longer the distance, the sound is going to get lost, or the amount of sound that you would hear will be lost over a long period of time. So again, that is another observation that we will have when we think about analog signals. So with those sort of disadvantages and things with analog signals, let's look at digital signals and how some of those things may be addressed with when we are using digital signals. So the main differentiation about digital signals is going to be, we can look at that using the same aspects that we identified with analog signals. So the first one is, in analog signals, we had continuous values. So over a period of time, we had values continuing over the whole period of time. But with digital signals, we will not have that. We will rather have only values at certain intervals. We will only have values at certain intervals, which we would identify as the sampling rate. We'll come to that a bit later. But we will only have a discrete amount of values in a digital signal. Then with each of those observation points, or each of those discrete values, we will still have a finite ranges of values possible. So again, in analog signals, we said, say, if the speed is changing between 10 to 20, all the infinite values in between 10 and 20 are possible there for an analog signal. But for a digital signal, it will, depending on the system, depending on the conversion and stuff, only a finite amount of values will be possible. Say if we are going in steps of 1, then the only possible values between 10 and 20 in a digital signal would be 10, 11, 12, and so on. Likewise, we will go in steps of 1, but it will be a finite range of values. Because we have only a finite ranges of values and we have only a discrete amount of values, we are not going to have exact values at all points in time as we had with analog signal. So in certain points, we may not have the exact value as we could have in an analog signal. So for example, as I previously mentioned, if the actual speed is say 10.5, then it will have to be rounded up to something that is suitable in that particular analog signal. So again, we will not have exact values as we would have in analog signal. And one of the common ways that we would represent digital signals is using binary. So we will normally use discrete values using binary in a digital signal. So now let's look at how we can take an analog signal and convert into a digital signal using what is called analog to digital conversion, or ABC. There are three main steps to analog to digital conversion. That is sampling, quantization, and coding. So if you look at the previous explanation and the main differentiation between analog and digital signal, these match with those points. That is, sampling is over a period of time. What we would do in terms of sampling is we will go and we will make observation at a fixed interval of time. So that is the sampling. And the interval that we take is what we call as a sampling period. So say every 1 second or every 1 minute or every millisecond, we will go and observe what is the value in the original analog signal. So say this is the analog signal that we have. So that analog signal will be there as it is. It is sound, for example. So then if you want to convert it into digital, we will go and observe at every suitable point in time or every interval in time, and we will get a value for that. So we will, for each point, we will go and get a value. So whenever at that sampling point, we will go and read what the value is from that analog signal. So that is sampling. So then once we get a sampled value, another differentiation that we had with digital signals is they don't have infinite values, because when we sample, we are still going to get infinite amount of values. So we need to convert that into a finite amount of values, and that is what we do by quantization. So here, for quantizing, what we would have is we would have a fixed amount of possible values that we can have, and with these fixed values, whatever the analog observation will have to be rounded to the nearest quantizable value. So similarly, how we had say 10.5 in the speedometer was converted and shown as 11 in the speedometer, you will have to convert that to a closest value that is available in that finite ranges of values. So that is the two main steps that we would take when we are doing analog to digital conversion. The third stage is what is called coding, and that is essentially giving it a binary value. So once we get it converted into a quantization, then converting that into binary is what is called coding. So if we again look at sampling, for example, what we do is we go and observe the analog signal. So we have the analog signal and we will observe the analog signal. And at each point in time, we will go and find the sampled value for that analog signal. So that is essentially it. So say if every 1 millisecond, we will go and observe the signal, or every 1 second, we will go and observe the signal. So that is the sampling period, and the inverse of that is what we may call as the sampling frequency. So that is how many values that we are going to get within a time period. Then quantization is basically converting that whatever the sampled value into a finite ranges of values. So say if we have a speedometer that can only display let's say every 1 or a single digit change is what it can show. So any sort of fractional values will have to be rounded into suitable digits closer. So that is quantization. So either this will be 10 or 11. So that is basically what we do with quantization. So we convert the sampled value into one of the possible values within the range. And that how many possible states or finite states are possible in quantizing will depend on how many bits that we are going to use in a converter. So again, the basic binary, if we have say 2 to the power 3 bits, or if we are using 3 bits, then that means we can have 8 different states. So 2 to the power 3, 8. So if we have say 4 bits, we can have 16 states. So the number of bits of our analog to digital converter would depend on how many states are possible. So this is how many bits we are going to use for each sample. So then the quantization size will depend on that. So that variation. So we'll look at that with an example here. So say we are using a 3-bit converter, and our original signal is between 0 and 10 volts. So those are the 0 to 10 volts is the range in our analog signal, and we are going to use a 3-bit converter to convert. So with a 3-bit converter, what we can have is actually these are slightly wrong, but the idea is we can have say 3 bits. We can have 3 bits. So 3 bits will give us 2 to the power 3, 8 states. So if we have 8 states, we will get the quantization range as this. We'll divide the quantization range with the possible number of states. So now what we will have is these 8 states. So now what we would do is, say if we are observing a signal, let's say we are observing yes, we have sampled and we have observed the signal. So this is the signal that we have observed. For each of these samples, we are going to get different values. So let's say the first one, we sample and we read 2 volts. So then 2 volts is going to be in this range. So it is going to get the state 1. So then we are getting a 3 volts, and 3 is going to be in this range. So that is going to be that. So now we get a 3.5. 3.5 is also going to be in this range. So that is also going to be the same. So similarly, we will take observations for each sample and find out within which of these ranges of discrete voltage ranges that is going to fit, and then we will get the corresponding output state. So that is basically quantizing. Once we have done that quantizing, then the last stage is encoding. It is basically assigning a suitable or equivalent binary value to that. So each of those output states we can represent depending on the number of bits that we had, because the number of bits that we had, 3 bits, it's a 3-bit converter. So we had 8 states. So then those 8 states will have 8 different binary values. So that is the basic idea there. So then we will convert them. So for example, these conversions like 1 to 2, that will be converted into, so that is the binary, that is going to be the binary stream or the digital signal for this conversion. So we started from an analog signal, we sampled, quantized, and we get a digital output. So then when we think about how we can do these conversions, what are some of the different types of ways to do this conversion, there are again a number of approaches, a number of systems or number of circuitries that are there to do this. We'll just look at one for an example. We'll look at flash ADC. So the basic idea behind flash ADC is based on a voltage divider. So you have a voltage divider that is going to divide the range of voltages and going to function as the quantization aspect of it. So the reference values will be given through this. Whatever the input voltage will be compared with each of these voltage states, and based on those comparators it will produce a binary output there after the encoding part. So it will do the quantization and encoding all in one. So, but this one is basically 2-bit analog to digital converter. So now let's look at some of the issues that we would have when we are thinking about analog to digital conversion. Let's take the signal that is shown on the screen as an example. So say this is the signal that we have, right? If this is the signal that we have, now let's think about how frequently we are sampling. Let's say we are sampling only at this frequency, or rather this frequency. So if I sample at that frequency, and then if I plot the resulting thing, it is going to be a totally different waveform. Because I sampled and I recreated the waveform, now it is totally wrong from the original one. So again, if I sample at this rate, again it is still a fairly wrong type of a signal. So one of the problems that we'll have is we'll have to have a suitable sampling rate, otherwise we will come to a problem known as aliasing. So aliasing is after analog to digital conversion, the resulting signal is significantly wrong. The reconstructed signal would be significantly wrong because we had less number of samples. So the basic rule there is we should have at least 2 times the frequency of the original signal as our sampling rate. And the best case would be 10 times the frequency, but at least we should have 2 times the signal frequency for conversion. Say, for example, if this signal is originally, say, 100 megahertz, then our sampling rate should be at least 200 megahertz. So that is the basic idea to avoid the problem known as aliasing, where we get waveforms that are totally not representative of the original waveform. So we should have at least 2 times the frequency as the 2 times the frequency of the original signal as our sampling rate. So a good example to you may come across this is music, that music files, sound files on computers. It is commonplace that you may find them using a sampling rate or a sampling frequency of 44,000 something hertz, or 44,000 or 44 kilohertz. The reason for that is humans can normally hear sounds up to 20,000. So if we double that 20,000, we get 40,000. Then we have a bit more. We end up with 44,000. Similarly, if we think about telephone, for example, telephone is normally intended for voice signals, and most human voices are around 3,000 hertz at most, 3,000, 3,500 maybe. So around that range. So it is okay to use a sampling frequency of 10,000 for a telephone signal. But the problem is, if you have such a signal, such a telephone signal that is using 10,000 as a sampling rate, and you send some sound that has higher frequencies, then that is going to be impacted by that. So this is something that you may observe when there are certain music played through certain telephone systems, like waiting sound, or when you call a call center, it may be playing some music and they may sound a bit odd because it is impacted by the issue of aliasing, because the original sound that is there is beyond the double the sampling rate there. So half the sampling rate there. So that is the main sort of aspect of aliasing, and how we can avoid that is using double the frequency of the signal as the sampling frequency. Another bigger problem that we would have with analog to digital conversion is what is called the problem of significantly higher data size being needed once it is converted. So that is, let's again take the example of sound. And as I said, then a common place to use 44,100 as the sampling rate. And again, 16 bits as the resolution for each quantization. There will be, we will use 16 bits. So for encoding, so we will have 65,000 possible values, so quantization states. And then for each second, we will produce this number of bits and in bytes. So per minute, it is going to be 5 megabytes of audio. So this is uncompressed audio, like a WAV file, for example. But one of the things that we can do to reduce the amount of this is, one, we can change the sampling rate. So that is what we do in terms of when we are thinking about telephone signals, because it is only the main intention there is to carry human voice. That doesn't normally need 44,000 as a sampling rate. So we may do something like 10,000, and that would be good enough for a voice. Or some other signal, like say, for example, speed of wind, for example, because speed of wind doesn't change as much as the speaking or music or sound. So then there we can have a resolution or sampling rate much less than what we may need for a sound waveform. So again, one of the issues with sampling is we may need a lot of space to store, and depending on the type of signal, we may have to choose an optimal sampling rate and optimal resolution to achieve a optimal data size. Now let's look at digital to analog conversion. And with digital to analog conversion, the main idea is just doing the reverse. So our digital computers or digital computing systems have processed and produced some digital information that needs to be transformed or translated into something that can be sent over to an analog signal. So we need to produce an analog signal. So the basic idea is we will have these sampled values, so discrete sampled values. Then we will have to somehow convert that back into an analog signal. So we start from a finite number of values in our digital signal, and the resulting analog signal should have somehow infinite amount of values. So hence it will be an analog signal. If we think about a very simpler way to doing this, if we say we have these two sample points as our, or like a few more points as our sampled digital signal points, we can just have these fixed values along that period of time to create an analog signal. Or we can just connect them this way, so they are sloping up and down between those points, but still we create an analog signal. After that conversion, each of these points will have infinite amount of values and all that, as with any analog signal. There are a number of approaches again for converting digital to analog conversions. Things that are known as decoders or binary converters. So there are different type of circuitries to do these conversions, and a lot of these you may find in microcontrollers and so on. So these type of converters will be present in those as well. So again, we'll look at a very simple example for conversion, what is called a decoder method or a resistance voltage divider method. So here, what we are doing is we are again using a voltage divider, and based on the binary input for each of these states, we will selectively switch a different voltage value. So then that would create different voltages at that different points. So that is a voltage divider mechanism. So we'll use the decoder to select between these states. It's a fairly simple approach, but the problem is, say now if we need to have this circuitry repeated for each of the states. So here for a 3-bit, we had say 8 states. If we have 4, we'll need 16. So likewise, for a 10-bit, we will need 1024 states. Would be a significantly larger and impractical circuitry to use. For smaller converters, this would be a fairly simpler option there. Another approach is what is called a R2R ladder. So again, in a way we use a similar approach in terms of voltage dividers, but here we are taking it in terms of our bit values rather than our states. So the number of circuitries are significantly lessened, and actually you can get a bit detailed explanation of how this particular circuit works through this. But it's not our focus in this lesson anyway. So, but you may find these different circuitries in different microcontrollers and so on, and you could choose depending on what is best needed. Like how many bits, and so on will be the factors that you may use for choice between one or the other. Now, let's look at some of the common types of hardware components that you may use with these systems, where you may have this type of analog to digital conversion, interfacing, and so on. So again, when we think about these type of components, they can fall into a large number of categories. When we are thinking about components that we may interface with in embedded systems, they can be electrical components, some electromechanical components, sometimes even purely mechanical components. So depending on what we are doing, what we are trying to do with these systems, depending on the type of embedded system, the nature of system it is trying to control, we may have different types of interfacing components and things. But we can broadly categorize these components into a number of groups. The first one is called sensors. Now, sensors are basically devices that will receive and respond to signals. So, for example, a temperature sensor is something that will receive or the temperature information in that environment in the form of a signal, because temperature is changing. Anything that is changed and observed is a signal. So changing temperature in that environment and react to that and produce some output. So it could produce a voltage variation or things like that, depending on the sensor, may produce something of that nature. So depending on the type of sensor, it may detect that change, and then it will produce some information in the form of an analog signal or a digital signal. So they can detect a signal and then as a result produce another signal. So for example, it may observe the temperature variation as a signal and produce a voltage variation as a result, and then we may use that for other observations. Say a microphone, for example, will observe the sound variation as a signal and produce a voltage variation as an output. So again, that is what we would use to observe. So we would start with some stimulus in the physical medium, some change in the physical environment. Then it would go through a sensing element and it would produce a voltage variation, something that we would identify as conditioning, and then we may use that information and use it as our observed signal. So we have a stimulus that is producing the change, and then we could observe that as a signal at the end. There's a basic transfer function that we would have with the sensors, for example. Again, we are not going to go into more detail on this, but the basic idea is many sort of sensors will have what is called a stimulus value at 0. So say so it may have a constant like that, and then a proportional component proportional to the stimulus there. So it's not just the observed signal or the output signal is not just always proportional, directly proportional to the stimulus. It would be, but there may also be some additional constants that may be there that we may have to take into account. So like what is the value there at the stimulus point is 0, for example. Say if we just as an example, if we say if you have a temperature sensor and it is producing, say at 105 degrees Celsius, it is producing 42.3 millivolt, and we also observed a zero voltage at 0 degrees Celsius, then if we use that uh, as part of our conversion in our function, and if we want to find the temperature at, if the observation is 15.8 millivolts, what is the temperature, then we can use that equation, substitute the values as we know, and calculate the constants and all these values. And it's a basic arithmetic, there's nothing complicated there, but what I'm trying to say is you can, this is how you may do conversions in depending on the type of sensors that you're using. And particularly when you are building embedded systems, when you are using various sensors, these are some of the things that you may have to do in terms of computation inside your microcontrollers, inside your microprocessors and whatnot. So, depending on the type of the sensor, depending on the information that it is produces, you will have to do some of these computations, calculations inside your digital computing components. Then we'll look at some of these common types of sensors that you may come across, like thermal sensors are very fairly common, like thermometers, which can actually output temperatures, sometimes in the form of voltages, depending on the nature of the. You may have things like thermocouplers, where change of temperature may affect depending on different types of metals and so on. Calorimeters, so, different types of thermal sensors are there. Then a lot of mechanical sensors, again, you may be familiar with quite a lot of these. Things like pressure sensors that can measure pressure on a surface, for example. You may use that even to measure weight and things like that. Barometers are there to measure atmospheric pressures, altitude measurements, flow sensors, particularly liquid or gas flow sensors, you may use if you are building an embedded system that is to do with measurement of flow of liquids. For example, you may have to use an appropriate flow sensor. Accelerometers, again, we find accelerometers a lot in most of our mobile phones these days. But you can get accelerometers as separate sensors and use, again, as part of your embedded systems and so on. Electrical sensors, again, anything that you can observe that is relevant to electrical signals. So you can measure resistance, voltages, currents, or the total energy consumption. So again, it's a sensor that is observing a phenomenon about that particular physical change of electricity in this case. You may have come across chemical sensors, particularly things like oxygen sensors or carbon dioxide or particularly carbon monoxide sensors. People may use carbon monoxide sensors inside environments where there's chance for combustion, not so much here, but like if you are using fireplaces, it is a good idea to use carbon monoxide sensors to see if it is in a dangerous level because it is poisonous. So again, we may use such sensors as well. Again, with most of these sensors, they may produce either some digital output, sometimes they may produce analog output, and then you may have to do the conversion within your A to D converters and so on. Then there are again various sensors like optical sensors, acoustic sensors, and so on. So there are various types of them. These are just some examples to sort of illustrate. Then another type of device that we may find when we are dealing with these type of hardware components is what we can identify as a transducer. So a transducer is basically a device that is going to convert a particular energy form into another energy form. Say, for example, if we take microphone as an example, microphone is taking sound as an input. So it is the sound energy that it is taking in. Then it is producing electrical impulses. So that it is producing electrical energy as output. So on a speaker, the reverse is happening. It is taking electrical energy and it is producing sound impulses. So for example, a solar cell converts light into or light or heat, depending on the nature of it, into electrical energy. A bulb, for example, does the reverse of that conversion. But all of these things are taking one form of energy and converting it into another form of energy. So it is mainly about converting of the energy. That is what we would identify as a transducer. So again, we can look at some of the different types of transducers. There are electrochemical transducers, things like batteries, fuel cells. So these are in a battery or a fuel cell. We basically what we have is we have some chemical energy stored in that, and then that is converted into electrical energy. So we have such conversions happening in those transducers. Electromechanical transducers, things like generators and motors and things like that. Again, here they take one form of energy. Say, for example, a motor, for example, takes electrical energy, converts it into mechanical energy, and a generator, for example, takes mechanical energy and converts it into electrical energy. So there's electromechanical transducers. Then things like electroacoustic, electromagnetic, electrostatics. Again, these are different types of converters like speakers, microphones, all these things. Then there are photoelectric transducers, thermoelectric transducers. Again, different form of energy conversion is what's happening. Then within transducers, there will be another subcategory of devices that we would identify as actuators. So the main point about actuators is they actuate or move something. So here the converted energy is in the form of motion or kinetic energy. So if it is converting electrical into motion or mechanical energy, then that is what we would identify as a transducer. But basically, an actuator is a subtype or a specific type of a transducer. So, for example, a thermal actuator, like if you think about a bimetallic strip, for example, based on the thermal changes, it is going to move. So there is a movement is happening. So basically, that is an actuator. Electric actuators are things like motors or solenoids, for example. So again, they take electric energy and then convert it into motion. So then they are electric actuators. We can have mechanical actuators like, say, screw jets, for example. So again, they convert mechanical energy into another form of another directional mechanical energy and so on. So they can also be categorized as mechanical actuators. Then we have hydraulic or pneumatic actuators, again using hydraulic fluids or compressed air. Again, if they can lead to movements, they can be categorized as actuators. So basically, all of these things, sensors, transducers, actuators, all of these things, these are components that you are going to interface with your embedded systems. Some of these would produce analog information that you may have to convert inside your digital computers, inside your microcontrollers. And some of these, if you are giving some information, again, you may have to give them in the form of analog signals. Again, you may have to do some analog to digital, rather digital to analog conversion. But in practice, you may find some of these devices with built-in analog to digital or digital to analog conversion. So for example, there may be some temperature sensors, the sensors themselves will have the analog to digital conversion part. So what you would get from that sensor is a digital information about the temperature. So not a voltage value, but rather a digital information about the temperature. So some of these sensors, some of these transducers, you may find them that can be interfaced using digital interfaces, but others you may have to interface with analog interfaces. So you will have to use these analog to digital and digital analog conversions within your uh, systems, within your digital systems or within your microcontrollers. Then when we think about continuous signals and analog signals and discrete signals, there are sort of common sort of things that we already looked at. So that is, say, analogs are continuous, digitals are discrete signals. The main sort of disadvantage with analog signals is they can be deteriorated over a period of time due to noise, but digital signals are fairly immune to that over transmission, long periods of transmission, uh, and things like that. Then in terms of bandwidth, again, if we transmit analog signals as analog signals, they will not need a lot of bandwidth, but the problem of data deterioration is there. But in digital transmission, it will need a significantly higher bandwidth in some cases, in many cases. Power consumption is a bigger factor again for choosing digital systems. Again, they will not need a lot of power. Then in terms of error, again, because of these the way these devices are built and so on, that is also an aspect. Again, digital systems can be less prone to observational errors, but they may be prone to sort of certain other types of errors like conversion errors and things like that. So as examples, like again, any physical phenomenon that we can observe in the physical environment can be represented in analog signals, and then a digital representation of that could be what we would see as digital signals. So these are some examples for common sensors and transducers for your reference. So that's all for today. We mainly looked at analog systems, analog and digital systems, analog digital signal conversions, and some common hardware components, different types of hardware components that you may be interfacing with your systems. So